to recap, we saw some examples of algorithms. Well, first of all, we fixed the architecture. So in this course, whenever we talk, if you want to talk about the translation between number of steps, number of instructions and time, actual time, then you should just multiply by nanosecond. Okay, so number of instructions or number of steps you multiply by 10 raised to minus 9, which is here in the slide, which is asking when is an algorithm efficient. So whatever is the number of instructions, we will multiply it by a nanosecond, and then you will get accordingly the time in seconds. I mean, this translation you don't have to do all the time. After a class or so, we'll only care about number of steps. But since you are all non-CSE students, so you might be more practical than CSE students. So for practical considerations, if you want to actually count seconds, this is how you can do it. Most of the time this analysis works. If your architecture changes, you have to change this calculation also. Depends on your architecture, but these days nanosecond is what you get for an instruction. And I don't think you can make it much faster than this. It's a hardware constraint. So the first example we picked is this famous sequence of Fibonacci numbers, which is given by, you start from 0, 1 and then you add the previous 2 to get the next number. We showed that this is growing very fast. Okay, so in 100 iterations, or the 100th number in this sequence is at least 1.5 to the 100. Okay, so it grows very fast. This is called exponential growth. So we saw several programs for this. First is the iterative fib. First is in the idea. So first is iterative fib, which will take n steps. It simply follows the definition of Fn. Second is recursive fib, which is instead of storing it in an array, it actually calls the recursive subroutine. And surprisingly, it is much worse. This takes exponential time. Second example we picked is subset sum, which is given an array of n integers and a special integer s. You have to check whether the special integer s can be obtained as a sum of some subset of the array. Is there a B of subset of A such that sum of small b's is s? Right, and this problem you can improve on the brute force, which is 2 raised to n, slightly, but not by too much. This is an open question to improve it much better. Okay, so any questions till now? That is where we stopped. So now we can look at another problem, which is example 3, which is of a different type. So this is the problem of sorting. Right, so the question here is, you already know. So here you have to write a program which takes as input array A of n integers, and in the output you want to sort it, let's say in ascending order. So ascending means that the values in A is the array. So in the same array you want to shift the values so that they go from smallest to largest. Yeah, so what are the ideas for this? Have you seen any algorithm? Quick sort. What did you say? Merge sort. Yeah, okay, so you already know the fast algorithm, so those are the fast ones. So first idea is you want to compare pairwise and swap. So basically you can start from the first element and add second element in the array. So you can do this iteratively by a for loop. So when you are adding the second element, if it is smaller than the first, you should swap, right? And so on. So when you get to the ith stage and you are adding the I plus 1th element, then if it is, let's say the I plus 1th element is smaller than the ith one, you should then swap it. And you should go as far as needed, right? So this is called, this can be seen also as insertion sort. So the idea is to add the new element, I mean go iteratively from element 1 to element n, and in every iteration you try to find the location where it should be in the previous work which you have done, right? So you are basically inserting the I plus 1th element in array 1 to I. So what is the number of steps in this if you implemented this simple idea? N, yeah, so around n square. So we can record that. So number of steps needed in insertion sort is, I mean essentially it's in ith iteration. What is happening is when you are adding the I plus 1th element, there are I locations which it can possibly be present, can be put. So you have to go, in the worst case you have to go that far. And this I goes from 1 to n, right? So this is around n square by 2. So we call it n square, which is not considered good because, I mean it is certainly better than 2 raised to n by 2. But this sorting is such a common problem. It is used almost in every computational code which you will write. For example, in Excel also, you just click a button to sort on a column, and it can do that in milliseconds, right? Even in big Excel files, it is immediate. So, you want to do that also on your smartphone. In your smartphone, you open an Excel file and then it sorts immediately. So this is such a common problem that if it was n square, then already in, let's say, 100,000 rows or 100,000 elements, n equal to 100,000, square of that will be tremendous. Okay, so it will be a very slow algorithm if you actually implemented this. So you want something better than this. So that brings you to the one you were mentioning, merge sort. So which is, the paradigm is called divide and conquer. So basically, it's conquer part is the merge part. Okay, so what you do here is divide into halves. Sort each half independent of the other, and then so now you have two sorted n by 2 arrays, sub arrays, and you merge them. Right, so this seems to be a more complicated algorithm than the first one. First one was almost by definition and iterative, just single for loop or maybe double for loop. This is more complicated because here you are sorting twice in every, I mean you are basically recursing in every step you are recursing, you are sorting 2 times. So it is definitely harder to implement. There are more corner cases here to deal with, but this is where mathematical analysis will help. If you analyze this, it's a much faster algorithm. Okay, one which we'll want to implement in smartphones to sort in an Excel file. So, so this is the famous merge sort. And what is the number of steps in this? Yeah, so it is not trivial to analyze, but I am going fast because I am sure you have already seen it. I have only accepted smart students, so I expect that you already know all these things. So this recurrence looks something like this. So Tn is basically 2 times Tn by 2 and the magical thing is that this merge is only linear time. Okay, so the time number of steps, if you call it Tn, it's basically double of the, each half, that is T of n by 2. So currently T of n is unknown, but this recurrence is known. If you solve this, then you will get that it's n log n. This is what you get around. This Lg will always be in this course log to base 2. Okay, so this complexity is some constant multiple of n times log n, which is extremely fast compared to n square. So this is the preferred way to sort big arrays. Right, so divide and conquer is a very useful paradigm. It is used to design algorithms. It is used to rule countries, and it was a very useful tool in colonialism also. So everywhere it has applications. In this course, we will see more applications, how to use this to solve problems. And it really gives fast algorithms which have these strange complexities. Right? For example, why is there a log n present here? N is the number of integers in your array. Why should there be a log n present? It's a very strange function which is present here. So it's an advanced technique, and it appears in interesting ways. In fact, many times you will not know that this will work. So it needs some practice how to use this in actual problems. Yes, so the obvious question is which one of these is better, and that depends on your n. So for example, just to get an idea, if you take n to be 10 to the 7, okay, so which is 10 million integers, which is quite common. It may easily be present in a practical problem. How many roads or how many cities or how many citizens, 10 raised to 7 is always something that you will get in practice. And if you have to sort in that data, then the first algorithm will require time. So this n square is around 10 raised to 14, right? Which if you multiply by nanosecond, so this is 10 raised to 5 seconds. 10 raised to 5 is more than 28 hours. Okay, so just to sort your data, which is the first thing you might want to do, it will already take more than a day. Right? So this algorithm, the first one is this bad. And what about n log n? So n log n will be 10 raised to 7 multiplied by, what is log of this base 2? It's around 21, and then a nanosecond. So what is this? This is less than a second. Right? So this is the difference between insertion sort and merge sort. The difference is between 1 second and 1 day. Right? So depending on how you have designed your algorithm, how you have implemented it, it can change everything. Yes, so how do you design such algorithms? Any answers? You are given a problem, how will you solve it in a good way? Right? There are no good answers, it's a philosophical question. But since I am here to give some answers, so I'll say you have to have two things, which is one is creativity, and second is perseverance. Right? So you need to be creative, which means that you should either be born with great skills in designing algorithms, or if you are not born with those skills, then you should practice many problems. You practice, you see many problems, you see many solutions and try to learn how it is done. and summarize everything in terms of a few paradigms. Right? So what are the paradigms, what is the philosophy of solving a problem? So that hopefully will make you creative, and perseverance is, given a problem, you have to try to solve it yourself. Right? So get the first bad algorithm or bad solution, then try to improve it, and so on. So these days it is very easy to just ask ChatGPT or Bard or Google to solve it for you, but that will not give you any skills. Okay, so you can use it once you have acquired all the skills. Once it has become routine, you can use those tools. But if you want to learn, then you have to actually persevere. So that is what your assessments in this course will force you to do. That's much needed. So that is about algorithms and examples. Any questions here? This of course is very fast, but it gives you the main things which are happening in problems and in their algorithms, and why you need this analysis. Right? So we'll make it more and more mathematical and formal as we go along. But there is a requirement for that. It is not just for fun or for this course, but it actually changes the final solution. So let us now, so we have not talked too much about data structures, so let us now also see some examples of that, which probably is new for you. Very few ESC courses cover data structures. So I think the only data structure you have seen is array, or whatever you made in struct, right? Which again is actually a bunch of arrays. So in this course, we will see more advanced, more composite data structures. So what does that mean? Shorten it to DS. So it's basically just information stored in a formatted way. Okay, so it is just whatever database you have, or whatever in fact information you have, you store it in a way, in a formatted way, so that will cost some time, but it is seen as a one-time investment. So you make that investment so that the data is stored in a proper format, and then as more and more questions about that data come, you give algorithms for that. Okay, so it's kind of a policy decision that you make in advance. I mean, if you are starting a bank or if you are starting a startup, then how your data will be stored, this is a policy decision you have to make in the beginning. And it may affect many of your profits and your future problems which you are going to solve, because if you have collected data which is huge and formatted and put in a bad way, then in the future you have to reinvest time and money to reformat it, right? So you have to be careful when you are making this decision. So that is where data structures appear. So obviously array is the first data structure. And this we have already seen helped in iterative fib. Right, so in this algorithm, when we were iterating, we were storing the answers in an array so that we knew where what value is. So in the future, when we wanted to compute f of n, we could use f of n minus 1 and minus 2, which were stored somewhere else. So that was more useful than, for example, recursive call. Because in recursive call, we did not know what is stored where. It was all haphazard because it is left to the computer to decide. Right? Recursive fib means that when you make a recursive call, then the computer will create its own variables, its own space, solve the sub-problem, and then forget about it. Right? So that time and money is gone, but there is no information about what happened inside. So instead of that, array was a better data structure there. But what is better than an array? So something better than an array is sorted array. Sorting is even better. as you are building your DS or your array, if you keep it sorted, then certain things in the future can become faster, right, in comparison to if it was unsorted. So why is that? We haven't seen an example, so let's take an example. So this is the traditional example of directory, which I think these days is not very important. But there was an era when people will print a book which will have all the phone numbers in a sorted way, sorted by, for example, the name of the individual. Or what is still relevant is dictionary. Right? So in a dictionary you have words which are sorted, and it's a printed book. So you can see that it is much easier to find a word in a dictionary in comparison, in contrast to if it was not sorted, right? If these 1 million English words were just put in some arbitrary way, then you would essentially, for every word, you have to go through the whole book to find where the word is, right? In comparison to what a sorted dictionary does. So why is that? Do you know the algorithm which you are actually using here? Binary search is the algorithm, right? So that's the point which makes it faster. Suppose a dictionary has n equal to 10 to the 8 words, so 100 million words or names. So what you have to do is you have to write a program whose input is dictionary A and word S or string S. And in the output you want to say yes if and only if S is present in the dictionary. Or in other words, you want to reach the place where S is present in the dictionary. If it is not present, you have to say that this is absent. It's an illegal word, illegal string. Or if it is present, you say that it's a legal word. Right? So what are the ideas here? So first is just do it sequentially. Right, so sequentially search S in A. So sequentially means that you start from page 1 and then go to page 1 million. Right? Every page you read and see whether S is present or not. So if you were stupid, of course you would do that, but then the problem is that then you are reading everything. Right? Although you have a sorted array or a dictionary, still you are going through every word when you are only interested in S. So this stupid algorithm, the time is, or number of steps is around n. So here the thing is, when we make a claim about number of steps or the time complexity or how complicated the algorithm is, you have to look at the worst case, right? So it is possible that in some input S is on the first page, or it is the first string, so then of course you will find it in one step. But there are many cases where this word may be in the middle of the dictionary or in the end. So then you have to go either to n by 2 or to n, right? So there is this whole spectrum, and we always take the worst case possible. Okay, so you have to think in terms of what an adversarial input will be. So an adversary will give you an input which is hard, so that will be usually in the middle of the dictionary or in the end. So you have to basically say that number of steps is around n. It's not 1, it's not 10, but it's almost as big as the array. And if it is that, then of course in terms of time it means 10 raised to 8 times 10 raised to minus 9 seconds, which is again 0.1 second per query. right? So one query takes 0.1 second, but if you make 100 queries, then it will take 0.1 times 100. So this is not considered fast, it's actually very slow because you will be using it for many, many queries, and then overall your cumulative time is very high. So the faster method is, of course, what you have already seen, binary search. So you do binary search for S. As it is sorted. Right, so binary search means what? What is the first step? You have to directly go to the middle of the dictionary, right? So middle of the array. So you go to n by 2 basically. So here you have 1, here you have n. So you can directly go to n by 2 and then compare S with that. And that will tell you whether you have to now, so either you already have a match, then you stop. If you don't have a match, then you at least have a bit of information that S is either on the left, either it is in the first half or the second half. So suppose it is in the first half, so then you can go to this midpoint, right, and so on. So then you find out that maybe it is on this quadrant, so which is what? N by 4 plus, I don't know, 3n by 8. Right, so and you can stop there if you find it. So basically, like here, to go to the middle is one step, and then another half is one more step, another half is another step. So if you do this analysis properly, you will see that it will take only log n steps, because every time you are halving the space, and the overall space is only n. So n becomes n by 2, n by 2 becomes n by 4, n by 4 becomes n by 8, and so on. So you are actually very quickly converging from n to a point, and every time you are halving, right? So this is the log n complexity again. Again, this strange function log n, which you don't see in the input, it's just the way our analysis works. It's a mysterious function. So number of steps here is log n, which for 10 raised to 8 is only 24, around 24 times a nanosecond. Right, so that's extremely small. It's around 30 nanoseconds per query. Right, so there is a drastic fall in the number of steps or in time per query. So obviously you will use this, and for this what is needed is that while the dictionary is being built, or while as over time more and more newer and newer words get added, you have to maintain the sorted array, right? So that is the policy which you have to make in the very beginning, that as words come, I will maintain a sorted array. And once you make that policy decision, it's called a data structure. Okay, so now whatever happens, you will maintain this invariant. You will maintain this DS invariant. So that information, which was previously just a bunch of words, is now properly formatted, and formatting means that you have to, every time something new happens, you have to update. So that is the slight difference between algorithms and DS. So algorithms is what you do, and DS is what you have decided, how will the information be stored, and then you stick with that policy. So data structure stores data in the memory in a way that each subsequent operation So the operations, we'll call them query and update. Okay, so each subsequent operation is fast. So ultimately we want this policy, this DS to give us fast operations. They should be fast. I mean, there are two ways to say that it's fast. Either every query or update itself is fast, or maybe sometimes it is slow, but cumulatively it is fast. Right? So the first is called worst case fast, and the second, if sometimes it may be bad, but overall it is fast, that is called amortized or cumulative complexity, which we may study in this course, but that's not very important. We'll focus on always worst case. And of course, invariant is maintained. Okay, so this identifying the invariant will be important. In all your assessments, the proof that you give, the analysis which you give, you have to first identify, in already your proof idea you should identify why are you designing this DS and what is the invariant which you will preserve or maintain. So every step that you take, you have to show that the invariant is not violated. Right? So like in the sorted array case, as new elements arrive, and as you do query or you update, you can add an element, you can delete an element. You have to show that in every step the array remains sorted. It should never happen that the array gets unsorted or that invariant gets violated. Then if you don't do that, then your whole design is actually faulty. You may not get any marks, for example. Yeah, so that is the first primary example of DS. Sorted array. I can give one more example, or in fact a problem which uses this. Yeah, so the importance of sorting and DS in general cannot be overemphasized. It's, I mean, almost in all useful applications you will need to take care of it. So one example problem that we will see later, but I'll just introduce it here, is the problem of range minima. So here you have to write a program where the input is array of n integers, so it's actually a DS problem. It's not just one query, but as you are getting these integers, you have to ultimately output, rearrange everything, rearrange the integers and output a data structure for which the following property holds. So a fast data structure to answer queries of the type so you basically have to implement this subroutine called range minima given I comma j. So I and j are the indices in the array. I you can assume is behind j, less than equal to j, which gives you the minimum in that interval. So ai plus 1 dot dot aj, what is the minimum of that? Okay, these will be your queries. So range min ij finds the min of ai plus 1 dot dot aj. Okay, so these are integers. Notice that in the input I am not saying that the array is sorted, so it may not be sorted. Even if it was sorted, well, okay, if it was sorted, then this can be pretty good, no? Then the answer will be just ai. Yeah, so sorting will solve this problem immediately. So we'll see what we will do. We'll design a different DS for this in the future. So A, for example, can be this unsorted. So this is I equal to 2, and this is j equal to 4, and here range minima I comma j is equal to, yeah, so the min is in the middle, 34. Right, so this is a problem which is used in other, it is used as a subroutine in other, in many other algorithms. So we'll design a DS for this. So of course, I mean, you have seen that this sorting will be a sorted array will be a good DTS for this, but it will cost time and log n to actually design this DS and make the first query, right? So the question I think here is that can you do it faster than that? Is there a way to not spend this time of n log n? Because you are already given an array which is unsorted. So if you decide to sort it, then it will take minimum, it will take this merge sort time. So is there a way to avoid it? Is there a DS which can do faster and answer these queries? So this is used in computational geometry, string matching, and other algorithms. As a subroutine, this is called. So yeah, two ideas are, you can either just sort in n log n time. So then each query is constant time. Step number of steps 1. Yes. Yeah, I think that is an excellent point, which probably is the reason why sorting will not be a valid solution for this. So we have to see where this is needed. If it is needed in a problem where it is not allowed to change the positions of the elements, obviously you cannot sort. Yeah. No, but then the original locations will be distributed in a haphazard way in your sorted array. It will not be a contiguous interval. So you want an interval, right? So the interval was there in the original A. If you sort it and make it, let's say, B, then now this, for example, I equal to 2 to j equal to 4, this 2, 3, 4 locations in B will be arbitrarily placed. So yeah, so this mapping between, so sorting is not really a real solution here. So that is the warning, but sorting may not be allowed. Yeah, so that's an excellent point, which tells you that here you have to do something else. If you are in a problem where sorting is not allowed, you have to remember, or you have to maintain the integrity of the locations of the values also. Then, yeah, so you have to design a DS with this invariant, that location is not disturbed. Yeah, so with that constraint, then the only solution right now is do it sequentially. So that is the range min brute. So this range min brute solution or subroutine is you just find sequentially the min, because there is, I mean, if the values are unordered, then AI to AJ min can be anywhere. So unless you do a single scan, you won't have any idea what the min is. So this brute force thing will be sequentially search. Okay. So again, you have the same problem. This number of steps will be, you have seen this example by now many times. That number of steps in the worst case here is n, right? So the same problem, if n is 10 raised to 8 or so, then per query you are spending a significant amount of time. So this is not a good DS. Yeah, third idea is actually similar, but let me anyway say it. So third is range minimum matrix. So what you can do here is you can build a matrix n cross n, and in the ijth entry you can put the min, right? But the cost here is even more tremendous, because how will you fill the matrix? It's a big matrix. Even if you fill it, how will you store it? So store range min I comma j in the ijth entry of an n cross n matrix M. So if you do this one-time investment, then after that all the queries will be almost free, right? Because your n cross n matrix is computed and stored somewhere in a hard disk, say, and after that whenever you want to solve range min I comma j, you can just point to that location, right? So this is a one-time investment. But the problem is that this cost here will be prohibitively expensive, because if n is 10 raised to 8, then the matrix is 10 raised to 16. So nobody will pay you to do this. So the problem here is that both time and space here comes out to be n square, right? Because the matrix is already n cross n entries, and then obviously to compute the value you have to go to each of these places and then compute the value, which again will be almost n square. So both time and space here is n square, which is even worse than before. So it's 10 raised to 16 times 1 nanosecond, right? That's a one-time investment, but it's too high. If this was allowed, then of course the subsequent steps will be trivial, because every query you can just pinpoint a place in the hard disk and you have the answer. So that will just be a lookup. You are just creating a lookup table, but just this is too high. So that's the question which remains, which we'll solve in the next class probably, that is there a data structure that solves this, that solves range min in efficient time and space. Okay, any questions? Right, so since our time is almost up, yeah, so you have seen some interesting examples. Much of this is from your earlier courses, but here it will become slowly harder than this. So in this course you will see many paradigms of algorithms and many designs for DS. And many data structure designs. Right, and more importantly, in any of these things that we will do, there will be analysis. So we'll be doing almost rigorous analysis. So which means that the demand here will be significantly more than ESC 101, for example, because there you were not really expected to give proper proofs of the algorithm, how many steps it takes, or given two algorithms, which is faster and by how much. But here you have to do all those questions, you have to answer all those questions. So there will be almost rigorous analysis. I say almost because it will not be very accurate. I mean, we are not expecting you to analyze each and every line of your C program and say how many seconds it took, because it would be crazy and also impossible to do. But it will still be rigorous in the sense of asymptotics, which we will define in the next class. So there is a way to hide all these unpleasant things, like if I change the architecture by 2 times faster, or if I increase the hard disk 2 times bigger, then maybe my algorithm is faster by half. So this kind of constants, 2 or half or 10 or 100, these things we can abstract out. Okay, and we can talk about the essential complexity of the algorithm, which is basically as a function of n. So that is what we want to do. So this will be an almost rigorous analysis in asymptotic terms. So we'll see that next time.